Welcome. Today I'm going to talk to you finally about energy. It's really what physics actually studies. And I know it's taken us 25 weeks to get here. But it's important to remember that the idea of energy is actually really not easy to define. It has a very specific definition, and I'm going to tell you what that is in just a minute. But it's not something that you can point at and say, that's energy. It's really tough to put it together in your head that all of these different flavors of all of the different things that we're going to talk about that are under the umbrella of energy really are all going together. They do, and it works, and it makes sense once you wrap your head around it, but the initial point where you wrap your head around it actually is a little tricky, so I just want to make sure you got that. Here's the definition for energy. Energy is the ability to do work, right there. Now, this you already know the definition of, work. Work is equal to, and that's a scalar, right, is equal to the amount of force that you apply, which is a vector, times the change in the displacement, or excuse me, change in position, or what we call it the displacement, which is also a vector. So that's, of course, assuming they're both going in the same direction, assuming, or maybe they're going in opposite directions, assuming the force is somehow causing some change over that displacement. That's work. You cannot do work, though, if you don't have energy to pull from to do it. And so I want you to think about this for a second here. We have a system, and let's say system, I don't know what it is, doesn't really matter, looks like this, okay? And the system has energy inside of it. And let's say it has 2,000 joules of energy. Notice energy is measured in joules just like work. Because you can convert them backwards from one to the other and back, they're measured in the same units. So important to remember. Now let's say you make that system do work on something. So let's say there's another system over here. And you want work to go from one system to the other. And let's say the work that you do right here is equal to 500 joules. Okay, so this system initially had 2,000 joules, and then it did 500 joules of work on a second system. Now all of a sudden, this initial system, system number 1 here, can't have 2,000 joules of energy anymore because 500 joules of work were done on the other system, so they left. So in this case, then, the energy that remains, E2 here, is actually just 1,500 joules. So we used 500 joules of work, which came from our stored energy of some kind, and it left the system. Now this system over here, let's say initially it had 0 joules of energy, excuse me. And then 500 joules of work was done on it. So my question for you is, how much energy does it have in the later stages after this work was done? The answer is it must have 500 joules. So you're getting the sense that energy and work are interchangeable. And so you use a certain amount of energy to do that much work, and then if that much work is done, that much energy is stored in the object. That's the crucial idea. And so here's this me trying to say it in a very short way. Energy must be converted into work when work is done. And then that work is stored as energy later on. Now it can be stored as really 2 main types, right? So it can be stored as energy of motion, so making the object move faster, or stored as just kind of stored energy, and that usually is based on the position of the object, and we call that potential energy. So potential energy looks like this. It could be, let's say you've got an object you lifted to a certain height, and so you know that at some point it will fall if it's allowed to, but right now it's not. And so at that point, before it falls, it has this potential energy, like that, up there. It hasn't fallen yet, but it could. And you did work to lift it up, so where did that work go? Well, it got stored in as potential energy. So you're starting to see how potential energy is actually stored. It could be energy stored when you compress a spring, or it could be energy stored when you force electrons to be very close together, because they don't want that, right? Because they're both negatively charged, they push each other apart. But you force them together. And so it's really stored in the positions of the objects, the height above the Earth, the compressed nature of the spring when it wants to be spread out, the positions of the electrons sitting together. So here's the definitions, the mathematical definitions for each. Kinetic energy really is energy of motion, and it's based on two things. It's based on the mass of the object and how fast it's going. And so here we have it. Kinetic energy is K, capital K right there, is equal to 1/2 times the mass of the object times the velocity it's going squared. And when most people mess it up because they forget that squared, because they confuse it with P equals m times v, which is related but not the same. So notice in momentum, mass and velocity are both equally important. In kinetic energy, mass and velocity are not equally important. In fact, velocity is actually much more important because it is squared, whereas mass is just mass. In fact, there's a question on the test that asks that specific thing. Which is more important, mass or velocity in kinetic energy? And the answer, of course, is velocity, because velocity is squared. Potential energy, on the other hand, has a different formula. And if you look at it here, first thing you notice is that we've got a U. That's weird. So capital U is what we use for potential energy. Some middle school textbooks use PE and KE for kinetic and potential energy, but we use the actual variables that you might see, so U. Oftentimes, because there's lots of different flavors of potential energy, you may see a subscript by it. So if I use the potential energy for gravitation, I'm going to say U sub G. If I say the potential energy for a spring, I may say U sub SP. And if I say the potential energy for something electrical, I might say U sub E. So those are just 3 examples. So you get the idea. Anyway, the potential energy, as you saw up here, is just equal to the amount of work done. So this is the amount of work that you did to have to move the object. So when I lifted the object up, I stored all of that work in it as potential energy. When I pushed the electrons together, I had to do work, and that work then got stored as potential energy. When I compressed the spring, I did work on the spring to be able to get it to its new shape, and therefore that work that I did is stored as potential energy. And so you're going to see that the work, this work, is what gets converted into potential energy. One important case to note, and because it comes up very often in this class, and it's another formula on our sheet there, and that is the gravitational potential energy. So gravitational potential energy formula looks like this. U sub G equals the weight of the object, F sub G, times the height to which it's raised. Okay? So this displacement right there, I changed for height. It's really the same thing. It's okay. It's no big deal. In this case, because displacement is a vector, height just means upward, right? So it's not a big deal. I could use delta y in there if I wanted to, but I'm trying to keep it for what you might see in other classes. So F sub G, if you remember, is actually a formula we learned in the Newton's laws unit, and that's the gravitational force on the surface of the Earth is equal to the mass of the object times the acceleration due to gravity, which is that negative 9.81 right there. Meters per second, right? So subbing this in for this, we get the actual formula that you might see more often, which is U sub G is equal to mgh. And so this formula right here is one you're going to come across very often. And so it's extremely important that you remember to take a look at that. And if you're talking about potential energy for gravitation, to go ahead and use that on the surface of the Earth. That's all I've got. Oh, actually, I take it back. There's one thing. And I didn't list it off here. Well, I did list it here. There we go. It's mechanical energy. Mechanical energy is this sum of this kinetic and potential energy. And the reason why we call it mechanical is just that it's used most often by machines to do work. That's it. So, no big secrets there. If you have any questions, please let me know. Otherwise, thanks for watching.